Welcome and a very good morning, class. Today we are going to finish our chapter 3 that will be on the normal approximation. And we know that we have covered so far for chapter 3. The first one, we have seen how the experiments that following binomial, and we know that the experiment for binomial will follow certain characteristic, and we know there will be 4 characteristics that fulfill the binomial experiment. And we have also discussed about the Poisson probability distribution, where we know that certain experiment will follow this particular features, and you know by now what will be the difference between the number of success for experiment following binomial and the number of success for the experiments that following Poisson distribution. And last time in our class, we have discussed how we can solve an experiment that following normal distribution. And we have seen how this particular normal distribution is being solved using one specific what we call standard normal distribution, where you can have variety of normal distribution problems and you solve them using a particular standard normal distribution. And to finish up with our chapter 3, we are going to see how the normal approximation can be done. So last time we have discussed about the approximation, how we may have an experiment following binomial, and at certain characteristic of n, number of trial and probability of success, we can approximate this particular experiment to follow what we call Poisson distribution. Means that we have given a binomial experiment, but we solve them using Poisson approximation. And for today's session, we are going to see how the first one, we can see the normal approximation of the binomial distribution and the normal approximation of the Poisson distribution. So that will be finish up our chapter 3. Okay, so let us see the first case. That will be the normal approximation of the binomial distribution. So how does this came in? Okay, so we know that there will be certain characteristic where the approximation can be done. So for the binomial distribution, the first thing that you should check will be the n, the number of success will be greater than or equal to 30. And the second one, both. Please understood that you need to fulfill both criteria. That will be number of trial multiplied with the probability of success. You will have greater than or equal to 5. Same goes to probability of failure multiplied with the number of trial. You also get greater than or equal to 5. Means that for this particular approximation, okay, for the binomial to be approximate means that you use the normal distribution to solve the binomial. These 3 criteria need to be fulfilled. Okay, last time when you have binomial, you approximate using the Poisson, means that you have 2 criteria. It's either n is greater than 30, and the second criteria is either NP is greater than 5 or NQ is greater than 5. But for this case, the 3 characteristic need to be fulfilled. And how this can be done? Okay, so in this case, when you have checked all the criteria are fulfilled, then we know that the original distribution for this particular experiment is following binomial with the parameter number of trial and probability of success P. And to approximate how this become the normal distribution then. So X become normal, where the mean, we know that we are talking about the population mean, will be the number of trial multiplied with the probability of success, and the variance is equal to number of trial multiplied with probability of success multiplied with probability of failure. So that will be your new distribution following the normal. Okay, so please remember the criteria and then the approximation that is being changed or being transformed to what we call from binomial to normal. So this will be the thing that you need to understand. Now, since we are using the approximation and we know that binomial is from what we call discrete probability distribution, and we are using the continuous probability distribution to be used to solve the discrete problem. So in this case, we are going to use this what we call continuous correction factor in order for us to use this particular approximation. So what are the things that you need to understand, or why is this so? Is because of the things that I mentioned before, from the discrete to continuous, taking into account this particular what we call criteria. We are going to involve the correction factor for each of the solution that we are doing for the approximation normal to binomial. Okay, so what are the continuous correction factor that you may see afterwards? So it will be based on the what we call mathematical criteria that is being asked in the question. So the first one, you may be asked, what would be the probability of success equal to certain value? Or what will be the probability of success if the x is less than or equal to certain value? So this is case number B. For case C, probability of success is less than certain value, D greater than or equal to certain value, E greater than certain value. So, having said you have all the criteria that is being asked, taking into account of this particular function, you are going to apply the correction factor. What are the correction factor? For equal to, sign for equal to, it will be minus plus 0.5. So all the correction factor will take into account 0.5 value. So for example, if let's say we put x equal to certain value, so let's say we put x as px is equal to 6. So if you have these particular equations, so this equation need to be corrected, okay, using the correction continuous correction factor, and this become a new equation where you will have 5.5 less than or greater than or equal to, and this one would be less than or equal to 6.5. Okay, so that will be your transform using the correction factor, continuous correction factor. Okay, so what if you have px less than or equal to 6? Okay, px less than or equal to 6. So this become, okay, this become px less than 6.5. Okay, what if you have less than px less than 6? So this become px less than or equal to 5.5. Okay, D, what if you have px greater than or equal to 6? So this become px greater than 5.5. Okay, and if you have px greater than 6, this become px greater than or equal to 6.5. So these are the continuous correction factor that may involve in the transformation of your original equation to the new transformation using the continuous correction factor. Okay, so how to calculate the binomial probability using the normal approximation. So I think the more or less these things are almost the same as what we have done in our equation using the normal distribution or standard normal distribution. So let's look of this particular what we call notes. when we discuss directly on the example. Okay, let's look at the first example. Suppose that 5% of the population over 70 years old has disease A. Suppose a random sample of 9,600 people over 70 is taken. What is the probability that less than 500 of them have disease A? How likely the event will occur? So when you read certain questions, what should come into your mind is to analyze. Since you are learning about three probability distribution, that will be binomial, Poisson, and normal, and you know each of the characteristic of this particular experiment or distribution. So what should have come into your mind when you read the question? What are the given information? And that given information will direct you to the correct distribution that you should use. Okay, so in this case, class, for this question, suppose that 5% of the population over 70 years old has disease A, and suppose a random sample of 9,600 people over 70 is taken. What is the probability that less than 500 of them have disease A? How likely the event will occur? So for the given question, find out what are the information given, and from that particular information, you can relate to the suitable distribution that you have learned before. So in this case, you know that you are given the probability, and the probability is related to uh, the certain number of trial, that is 9,600. So in this case, what should come to your mind is we have what we call a random variable that follow probability, binomial probability distribution. And before we can find the distribution, what is the defined random variable for this particular case? And we know that x in this case is the number of success. And the number of success for this particular binomial distribution refers to number of people, okay, number of people over 70 years old, okay, has disease A. Okay, so that will be the number of success refers to. And this number of success is following binomial with the number of trial is 9,600 and the probability of success is 0.05. Okay, so this will be the two most important information that you should extract from the given question. And from this, you know that we are discussing under the approximation, normal approximation of binomial. So we know we need to check whether this can be approximate to normal or not. So we have to check the three criteria that will begin with the number of trial. So n in this case is 9,600, which is greater than 30. So this one is fulfilled. The second one would be the number of trial multiplied with the probability of success, which in this case 9,600 multiplied with 0.05, and from this you will get 480. Okay, and it is greater than 5, also fulfilled. And the third one will be NQ, 9,600 multiplied with the probability of failure, that will be 0.95, and in this case you will get 9,120. Again, it is greater than 5 and all the criteria fulfilled. So in this case, you can do the approximation, normal approximation, where your original x that following binomial can be transformed into x following normal with the parameter mean, that is the NP. Okay, so NP is 480 and the variance would be NPQ. In this case, it would be 465. How? This is N multiply with P multiply with Q. And for the mean, you can get from N multiply with P. So this is your new distribution for the normal approximation. And once you have got your new distribution, okay, go back to your question. what is the probability that less than 500 of them have disease A? So it will be Px less than 500, okay, have disease A, and we know that this is a problem of an approximation, normal approximation from binomial, and we know that binomial is a discrete probability distribution, and you approximate using the continuous probability distribution. So in this case, the correction factor or continuous correction factor involved. So in this case, as I mentioned before, for less than 500, when we apply the continuous correction factor, this become Px less than or equal to 500 minus 0.5, you will get 499.5. So this will be the first step. And we know that in order to solve for normal distribution, we have to transform the particular problem to the standard normal distribution, where we will refer to one distribution only, the standard normal. So when we transform, this become Pz less than or equal to, when we have transformed to the standard normal, so we have to transform as well the right hand side. That will be 499.5 minus the mean, that would be 480, divided by the standard deviation of the distribution, that will be 456 square root. Okay, so that will be the second step. And we know that the distribution for the original x, okay, you know that the mean is equal to 480, and you are looking for less than 500, which is at the right hand side, that will be the positive region. So let's say this is where the 500 is located, and you are looking for the probability value that covers this particular shaded area. So when we transform this into standard normal, okay, we know that the mean for the standard normal is equal to 0. And when we transform this to z, so what is the z value here? So continue from this part. So Pz less than or equal to, so if you calculate the right hand side here, you will get 0.9132. So then we know that the z that we are looking for here is 0.9132, and the area is covering this particular shaded area. So now, in order to get this particular area value or the probability value, we know that, okay, half of this region is equal to 0.5. So half of this is already 0.5, and the next part is finding the probability here. So in this case, we know that we have 0.5 plus the probability of z covering from 0 until 0.9132. So refer to your standard normal probability distribution, okay, for 0.91. Okay, using this particular standard normal distribution, you are looking for 0.91. Since the nearest approximation is from 0.9132, so we can approximate them to 0.91 only. So 0.91. So this is the probability value for the shaded area beginning from 0 until 0.9132. So it will be 0.3186. Go back to our note. So this will be 0.5 plus 0.3186. So this is 0.3186. So you will get the probability value is equal to 0.8186. Then you know that the probability of x less than 500 is given by 0.8186. But what does that mean? Okay, so in order to interpret how likely the event will occur, using 0.8186, it is equivalent to 81 or 82%. Okay, almost 1. So in this case, we may say that the event of less than 500 people age 70 years old have disease A is what? Since approaching 1, so it's highly likely to occur. So the chance is higher for the probability value or the event to occur. So that's how we solve for the first equation for the approximation, normal approximation of binomial. What if we have a equation reflecting the Poisson? Okay, so we know that Poisson only use one parameter, that will be the mean value or the lambda. So what is the condition that you should check? The condition is just lambda is greater than or equal to 10. Means that if your lambda is equal to 10 or greater, then you can have the approximation of normal to solve for the equations. And the same goes to what we have for the binomial just now. So how do we approximate them? So if let's say x, okay, again, if you're given x originally is following Poisson with lambda, so if we check that the lambda is greater than or equal to 10, then we can approximate to normal, where the new distribution will be x following normal with the parameter, the mean is lambda, and the variant also is equal to lambda. So Poisson case will be very simple, but again, bear in mind that the complexity of the Poisson will be back to the interval given to you in the equation part. Okay, so let us look at the example. If it is found that on average, one customer per 2 minutes arrive at a supermarket checkout counter. Calculate and interpret the probability that at least 33 customers arrive at the counter during particular interval of 1 hour. So look at the questions. So for Poisson, given condition at the beginning is one customer per 2 minutes arrive at the supermarket checkout counter. But the question asks you, okay, the interval become for 1 hour. So this is where you have to be very careful and you have to transform into the interval correctly. So how do we do this? Okay, now take out the information first. So in this case, we know that the only given information at the beginning is one customer per 2 minutes. So in this case, what is your defined x? X will be the number of success, that will be number of customers. Okay, customers, how many customer, number of customers in 2 minutes. Arrive at the supermarket checkout counter. Okay, so this x is following Poisson, which is the lambda is equal to 1, and this one is for 2 minutes. Okay, so then since the question asks you for interval of 1 hour, so in this case for 1 hour, so in this case you transform to 1 hour, x will be following Poisson. If for 2 minutes is one customer, then for 30 minutes it will be 30 customer. So for 60 minutes. Just do some maths over here, okay? So this will be your new distribution where your lambda change to 30 for the interval of 60 minutes or 1 hour. So let's do the equations. Calculate and interpret the probability at least 33 customer. So you have at least x. So x in this case will be, so in this case lambda is equal to 30, which is greater than 10. Okay, so the condition is fulfilled. So for the given question, you have to find at least, so at least 33. So this will be the probability that you need to find for this particular questions. Okay, and since this is an approximation for using the continuous from the discrete, so the continuous correction factor applies, and we know for this particular continuous correction factor, it will be x greater than, so 33 will be deducted by 0.5, so you will have 32.5. So that will be the first step that you need to do. Then we know that we have to transform that in using the standard normal. So using the standard normal, x becomes z, okay, greater than 32.5 minus 30, the mean, okay, divided by the standard deviation. So in this case, x is approximate to normal, it become n 30, 30. Okay, so the standard deviation will be the square root of 30. So calculate for z. Okay, so z in this case, if you calculate, you will get 0.4564. Okay, so if I were to draw the original distribution for this particular equation, okay, the mean is equal to 30. Okay, and you are looking for greater than at least 33 customer. So you are talking about 33 here. Okay, that will be the mean. Then the probability that you are looking for is over here. And if you were to transform this into standard normal, we know that standard normal, the mean is equal to 0. And for this particular transform for the standard normal, it will be z, where z is equal to 0.4564. And this is where the probability region is at. Okay, so in this case, how to find here? Whereas your given probability from your standard normal is for this particular area. So we know that half of the area, half of the region is 0.5. So we know that in order to find the shaded area here, it will be 0.5 minus probability of z from the area of 0 until 0.4564. Okay, so check for the probability value given for this particular region. So 4564, 0.4564, 4564 approximation, it will be 46. So 0.46. So from your distribution, standard normal distribution table, the probability value from 0 until 46, it will be 0.1772. Go back to your notes. Okay, so it will be 0.5 minus 0.1772. This is where the 0.1772. So you will get, in this case, you will get 0.3228 as the probability value. Okay, so how do we interpret this? This is almost 32% in terms of the probability. So how do we interpret this? So it is very small, less than 0.5. Okay, it's in the middle of 0.0, from 0 until 0.5. So we can say it is less likely. Okay, it is less likely that at least 33 customers will arrive at the counter, okay, during particular interval of 1 hour. Okay, so this is how we interpret the probability value. So this is how we can use the normal approximation given that the original equation is from the Poisson. So everything in order. First, take out all the information, then check whether the approximation can be done. If the criteria is fulfilled, then the approximation follow. And bear in mind, consider the continuous correction factor involved for that particular questions. Okay, so there are some exercises as well as extra exercises. So for the extra exercises, I'm not going to do for your information. From the extra exercises, there are questions related to normal probability as well as the approximation question. But before we finish the lecture, I would like to do the two questions that reflect the approximation, normal approximation for binomial and Poisson. Let's look at these third questions. A magazine reported that 6% of nation drivers use smartphone while driving. If 350 drivers are selected at random, find the probability that exactly 30 drivers say use smartphone while driving. Interpret the probability calculated. Okay, so let's check what are the given information. Since we have the probability and we have the number of trial, we know that this is reflecting the binomial distribution. So what is the x defined here? Okay, so in this case, x is equal to what? X is equal to the number of success. So number of success is number of Malaysian driver, okay, use smartphone while driving. Okay, so in this case, x is following binomial with the number of trial is 350 and probability of success is 0.06. So that will be your first two information extracted from the question. And looking at the number of trial is very big. Okay, we know that in order to do the approximation, three criteria will be need to be checked. Okay, the first criteria would be n in this case is equal to 350, which is greater than 30. So the first condition is fulfilled. The second condition would be number of trial multiplied with the probability of success. That would be 350 multiplied with 0.06. In this case, you will get 21. Okay, and this value is greater than 5. Then the second criteria is fulfilled. And the third one that you need to check is NQ. Okay, so number of trial multiply with the probability of failure. So 350 multiply with 0.94. So in this case, you will get 329. And it is greater than 5. So the third condition also fulfilled. Having said this, okay, then we know that the approximation can be done. So x become normal, the mean equal to 21 and the standard deviation is equal to 19.74. So this is NP and the variance is obtained from NPQ. Okay, so we know then the distribution of this particular equation is talking about the mean is equal to 21. Okay, now what is the question? Find the probability that exactly 30 drivers. So P X exactly 30. So you are talking about exactly 30. So let's say this is where 30 located, the mean. Okay, so using the continuous correction factor, I guess this is the easiest one to remember. So if you have equal to 30, so applying the continuous correction factor, this become Px greater than or equal to, sorry, greater than only, not equal to. So greater than 30 minus 0.5, it will be 29.5. But less than 30 plus 0.5, you will have 30.5. So, uh, uh, if you have exactly 30, means that, okay, what you need to find is the probability for the area for 29.5 until 30.5. So this is where the probability that you are looking for. Okay, so we know that using this particular approximation, solving for the normal, you have to transform into standard normal. So let us transform to standard normal. So this will be 29.5 minus 21 divided by the standard deviation, that will be square root of 19.74. Okay, x 30.5 minus 21 divided by square root of 19.74. Okay, so calculate for this. So if you calculate, you will get, okay, you will get 1.91 x 2.14. So if we were to draw the region using the standard normal, okay, so this is where the mean equal to 0, and this is where 1.91 until 2.14. 2.14, and this is the probability or the region that you are looking for. Okay, so applying whatever we have learned before. Okay, so we are looking for, okay, so we are looking for this region, the probability value. So p x, z. So this is also z, sorry. So this is z. So this is z. Sorry for the mistake. So this is z. Sorry, from 0 until 2.14 minus probability for this part. Okay, since we are looking for this, so p z 0 until 1.91. So let's refer to our standard normal table, and what will be the probability value obtained from these particular equations. So the first one we are looking for from 0 until 2.14. So looking for 2.14, 2.14, 0, 1, 2, 3, 4. So this is the probability, which is 0.4838, and from 0 until 2.14 minus the probability from 0 until 1.91. 1.91. So this is where the probability is. So let's put together into your calculation. Okay, so you will have here, it will be 0.4838 minus 0.4719. So you will get 0.0119. So interpret the probability, very small probability, which is approaching 0. So in this case, if you approximate, this is only 1% only. Okay, so how do you interpret? So it is impossible, okay, for exactly 30 drivers, okay, use smartphone for Malaysian driver, exactly 30 Malaysian driver, to be exact, Malaysian driver use smartphone while driving. Okay, so that will be for normal approximation for the binomial. Okay, for the last part, okay, for the last part, that will be the approximation, normal approximation for the Poisson. Okay, the average number of accidental drowning in United States per year is 3.0 per 100,000 population. Find the probability that in a city of population 400,000, there will be less than 10 accidental drowning per year. Now, this is a bit different from what we have had before. So if we were to, we know that this is Poisson, since you are given only one value, that will be the mean. That will be three people, three accidental drowning in 1 year. Okay, so originally So before this, before we further solve for this equation, define the x. So x in this case is what? Number of success for the Poisson. So there will be number of accidental drowning in United States per year. Okay, and for this particular case, it is reflecting for the population of 100,000 per population. Now x following Poisson, and it is equal to 3, and this one is for 1 year, okay, and 400,000 population. And the question asks for the population of 400,000. How does it transform into the new lambda? So since if for 1 year, 100,000, you got 3 drowning, accidental drowning, what about 400,000 population? So there will be increment of 4. So means that you have to multiply the lambda with 4. So your new lambda would be P Poisson 3 multiplied by 4, you will get 12. That will be again for 1 year, and that will be 400,000 population. Okay, so in this case, when you see the lambda is obviously greater than 10, so in this case, lambda is equal to 12, which is greater than 10. So the criteria to be using the normal approximation is fulfilled. Then we know that this particular distribution can be solved using normal, where the mean is equal to 12 and the variance is also equal to 12. Okay, so this is where if you plot down the distribution, the mean middle value is equal to 12. Now let's move to the equation. Find the probability that in a city of population 400,000, there will be less than 10. So Px less than 10. And applying the continuous correction factor, you will get what? Px less than or equal to, so it will be subtracting 0.5, you will get 9.5. First step. Second, transform into standard normal. So Pz less than or equal to 9.5 minus 12 divided by square root of 12. That would be for the standard deviation for the new distribution. So find for z, Pz less than or equal to what? You will get, in this case, negative 0.7217. So if you were to draw the standard normal, and you are looking for less than 10, so 10 is somewhere over here, less than 12. So let's say 10 is here, so this is where the probability that you are looking for. Okay, so if 0 is here, and you are looking for negative 0.7 and less, so this is where negative 0.7217 is located, and this is where the probability value that you are looking for. So how do we find this? Using the understanding that we have had before, using the mirror. So since we are using the right hand side from the distribution, so you will have 0.7217 here, and this is the area that you are looking for. So if you were to write down using the mathematical illustration, so this will be 0.5 half part of the area minus the probability of this x region. So that will be Pz from 0 until 0.7217. So this will be 0.5 minus, so from 0 until 0.7217. So if you refer to your standard normal table, 0.72. 0.72, so you will get 0.2642 for the probability value of the x shaded area just now. So it will be 0.5 minus 0.2642, and you will get 0.2358. So in this case, you will have very small probability value, which is less than 0.5. And we know that in this case, it is more or less 24% if you do the approximation, 24% of chance that the event will occur. So this is how we can solve for the normal approximation for the Poisson probability distribution. So I hope everyone can understand how the approximation, the Poisson approximation for the binomial, how to use the normal approximation for binomial, normal approximation for Poisson. So you have three types of approximation. So I hope you all can understand. If you have any problem, you can ask me or you refer to your recorded video